Around 480 million years ago, in the shallow pre-Pangea seas, something small and armored moved across the seafloor. Its front half was covered by a smooth, domed shield. Behind that, its body bent on a hinge. A straight tail trailed behind, like a drawn line in the silt. That animal left its outline pressed into mud that slowly turned to stone. And in the layers above, spanning ages, the same outline kept appearing. The shield, the hinge, the tail. While the creatures around it changed beyond recognition, this one barely edited its own design. Roughly 160 million years later, some of its relatives moved into the freshwater swamps, where forests of giant ferns were slowly becoming coal. Others stayed in the shallows of warm, briny seas. The Permian extinction erased most marine life on Earth, but the shape survived. In the Triassic, it grew larger, up to 2 feet across, and spread across the coastlines of continents that were still drifting apart. An asteroid ended the age of the dinosaurs. The shape kept turning up in the sediment. Fossils from the late Jurassic, 148 million years old, show juveniles that are nearly identical to the ones that today wash onto Atlantic beaches with the May tide. Ages later, 20,000 years ago, during the last ice age, a cold river valley cut across an exposed coastal plain, with sea level more than 100 meters lower than today. As ice sheets melted and the Atlantic crept inland, that valley flooded and became a broad estuary, tidal, turbid, rich with the mixing of fresh river water and salt. Marsh gripped the new edges. Sandbars shifted into barrier beaches. Within a few thousand years, there was a stretch of shallow, calm, gently sloping shoreline on the map of the world. Warmer than the open Atlantic shelf, protected from heavy surf, silty enough to feed on, sandy enough to dig into. When this bay took shape, it only took a second on the geological clock for the animal that had outlasted everything else on the seafloor for 500 million years to find it. The water of Delaware Bay arrives flat and silty. The color is weak tea laced with iron. It spreads up the sand in a slow push that smells of salt and marsh grass. Underneath is something older, the mineral breath of mud that hasn't been dry since the Holocene. The beach is brown-gray and coarse. Fragments of oyster shell lay exposed. Empty horseshoe crab shells, called molts, lie in lines. Translucent husks the color of caramel. They rustle in the breeze like old paper. A fiddler crab freezes at the edge of a tidal creek, one claw raised. It is late May. The moon is fat and climbing. Out beyond the low surf, something stirs. The bay shallows to barely a meter here. The bottom is silt and shell hash. A shape rises on the incoming tide, broad, domed, the size and darkness of a cast iron skillet. He is an Atlantic horseshoe crab. Despite the name, he is no crab at all, an arachnid, closer kin to spiders and scorpions than to any crab. His body plan has barely changed in 450 million years, a span so deep that when his ancestors first crawled across the tidal flats, the continents had not yet assembled into Pangaea. Nothing with a backbone had ventured onto land. He weighs perhaps 3 pounds, smaller than the female he seeks. His carapace has the shape of a combat helmet, smooth on top, rigid underneath, with the spiny bases of 10 legs. His compound lateral eyes each hold roughly 1,000 ommatidia, the tiny individual eye components that make up a crustacean's eye that look like a honeycomb. The cones and rods are 100 times the size of a human's. At night, a chemical signal from a clock in his brain amplifies their sensitivity 1,000,000-fold. Dim moonlight becomes enough signal to find a mate. 2 smaller additional eyes sit on the crown of his shell. They detect ultraviolet light. More photoreceptors run along his tail, synchronizing his internal rhythms to the cycle of day and dark. 10 eyes in all. And still, he navigates the bay floor less by sight than by feel. Receptors in the tiny hairs around his mouth taste the dissolved signature of this particular shoreline. His body senses the Earth's magnetic field, a faint orientation that he has carried since he first hatched and crawled into the sea. He rides the tide in. Ahead of him, a larger female pushes through the shallows. He catches her. His first pair of walking legs evolved into hooks, clamp onto the rear of her carapace. He will stay there, clamped to her for days. Behind them, more dark shapes rise on the swell. Pairs, trios, singles patrolling for other singles. By high tide, this stretch of bay beach will be paved with them, helmet over helmet. The largest spawning congregation of horseshoe crabs anywhere on Earth. A scene that has played out on shores like this for longer than flowers have existed. The pair pushes up the sand past the last foam line. He holds on. Over the course of this night, she may lay and he may fertilize 80,000 eggs. Clusters stitched along the upper beach like a buried necklace. The bay will decide which ones survive. Somewhere overhead, a red knot descends. A rust-bellied shorebird, barely larger than a robin. 9,000 miles into a migration that began at the bottom of South America. The crabs don't see it, but the knot sees the eggs. And for this bird, everything depends on what happens next. Our crab, still on the female's back, waits for the tide to turn. But before the tide finds him, something else does. A hand grips the rim of his carapace and lifts. The water falls away. His gills, 5 paired flaps beneath his abdomen, beat against open air. They're built to pull oxygen from water and struggle when they get dry. Now, they're drying quickly. He is placed in a container with others, shell against shell. He can feel their movement through the walls of his carapace, but cannot right himself. Hours pass. The salt smell of the bay fades and is replaced by something sharp and neutral. The air is cooler, steady. The light overhead does not move. Movement. He feels a painful pressure at the soft hinge of membrane near his heart, a thin, precise point that does not belong to any tide, any predator, or any signal his body has ever been built to answer. I'm David Maroney, and you're listening to the Wild Systems Podcast. Each week, we look at a conservation effort from somewhere around the world. We dive into the ecosystem and uncover the systems that drive it to endure in a changing world. We look at how conservationists are putting their finger on the scale to influence those systems, and the true data behind whether or not that effort is succeeding. I want to ask, why do conservation efforts succeed or fail? How is the wildness there being impacted? And how would the effort look from the perspective of those wild creatures we're trying to protect and preserve? Today, we're wading into one of the oldest partnerships on Earth. We're following horseshoe crabs onto the beaches of Delaware Bay, what they face when they get there, and what they leave behind. Picture the eastern seaboard of the United States, roughly halfway between New York and Washington, where the Delaware River meets the Atlantic. The land opens into a broad funnel. Delaware Bay, about 800 square miles of shallow water, turbid and enormously productive, a working estuary. A drowned river valley carved during the last ice age, slowly filling with sediment ever since. Its average depth is barely 24 feet. Its tidal range, 6 feet. Its water is perpetually cloudy, with suspended silt and plankton. This makes it one of the most biologically rich bodies of water on the Atlantic coast. Nearly the entire perimeter of the bay is fringed with salt marsh, over 200,000 acres of it, some of the most extensive tidal wetlands in the northeastern United States. Low marsh of smooth cordgrass gives way to higher ground of salt meadow grass. Behind that are brackish and freshwater marshes with even more plant diversity. The salinity shifts as you move, close to the level of the ocean at the mouth, below 5 parts per thousand in the upper reaches where the river's freshwater still dominates. Between those extremes lives a gradient of life. Blue crabs, American oysters, weakfish, Atlantic silversides laying their eggs at the vegetated edge. For a horseshoe crab approaching the bay from the deeper Atlantic shelf, the shoreline announces itself through senses much different than ours. The water shallows. The bottom shifts from sand to silt. Dissolved minerals change. A chemical signature specific to this latitude, this river mouth, detectable through the rhythmic throat pumping of the horseshoe crab. The magnetic field of the earth tilts and strengthens in a pattern he imprinted the day he hatched. His compound eyes evolved for one job, finding another horseshoe crab in the dark, silty water. The world he sees is a mosaic of light and shadow, a grainy, flickering map. A moving dome on the bottom means a potential mate. A dark overhead shape means danger. Temperature pulls him in. When the bay's water crosses roughly 11 degrees Celsius, 52 Fahrenheit, he feels a shift in his drive and begins moving shoreward. Spawning peaks between 15 and 20 degrees Celsius, up to 70 Fahrenheit. It is highest when the tides are highest, around the full and new moons of May and June. He reads the tide through pressure sensors in his body. He orients to the beach using wave energy felt through his carapace. Moderate waves guide him in. Heavy surf drives him back. The beach must slope gently, 2 to 8 degrees, so he can reach the high tide line without being rolled. The sand must be the right texture, coarse enough to drain, fine enough to hold moisture around the eggs as the tide retreats. This is their world. Marshes buffer storms. Oysters filter water. The bay produces astronomical volumes of plankton, which feed fish, crabs, jellies, and worms, which in turn feed horseshoe crabs on the bottom and shorebirds at the surface. And every spring, the horseshoe crabs return what they've eaten, back to the beach in the form of billions of tiny green eggs, a caloric deposit so concentrated, so perfectly timed to coincide with the northward rush of migratory birds. The Delaware Bay became the single most important refueling stop on one of the longest migration routes in the Western Hemisphere. Horseshoe crabs have been used by humans on this coast for centuries. An Algonquin-speaking indigenous people, the Lenape, harvested them. Colonial farmers grounded them into fertilizer by the cartload. And then, something changed. A shift in the bait market. American eel and channeled whelk turned out to be very effectively caught with horseshoe crab bait. Both were commercially valuable. Demand exploded. In 1991, the recorded harvest across the Atlantic states was roughly 100,000 crabs. 6 years later, by 1997, it had rocketed to 2.5 million. Fishers used 1 to 2 crabs per pot. They preferred pregnant females, the very animals carrying the next generation's eggs inside them. The effects cascaded. Horseshoe crab egg densities on Delaware Bay beaches had once reached 40,000 or more per square meter, but they plummeted. By the early 2000s, surveys were recording 5,000 per square meter, a 90% collapse in the food supply that an entire web of migratory birds depended on. The red knot bird felt it first and hardest. This small shorebird flies from Tierra del Fuego to the Canadian Arctic each spring, a round trip of roughly 19,000 miles. Delaware Bay is one of only 2 stops it makes on the northbound leg. 90% of the Atlantic population funnels through. The birds arrive in May, exhausted, underweight, burning the last of their fat reserves. They need to nearly double their body weight, adding around a quarter pound in 2 to 3 weeks, to have any chance of reaching the Arctic and breeding successfully. Their only fuel source at the bay is horseshoe crab eggs, dug up by wave action or by the spawning crabs themselves, lying exposed on the surface of the sand in astronomical densities. Or at least, they used to be. In the late 1990s, red knots took only 11 days to gain the quarter pound at Delaware Bay, the fastest rate recorded at any stopover in the world. By 2002, that feeding rate had increased to requiring 50 days, but they couldn't spend that long. Birds were leaving the bay too thin to breed, or not surviving the final push north at all. The population spiraled. A bird that had once numbered perhaps 100,000 declined toward the low tens of thousands. In 2015, the red knot was listed as threatened under the U.S. Endangered Species Act. Meanwhile, a second kind of harvest was growing in the background. Since the 1970s, the biomedical industry had been collecting horseshoe crabs for their blood, a milky, copper-based fluid that turns blue when exposed to air. The blood contains cells that produce a clotting agent, used to test every injectable drug and medical device for bacterial contamination. It became so crucial to testing processes that there is, functionally, no modern medicine without horseshoe crab blood. So what does this biomedical process look like? Crabs are collected from beaches and nearshore waters, trucked to laboratories, strapped into racks. A needle is inserted directly into the membrane around the heart. Up to 30% of the animal's blood is drawn. The crabs are then returned to the ocean. Industry estimates place post-bleeding mortality at 10 to 15%, but independent studies report rates closer to 30%. And that figure does not account for sublethal damage, reduced activity, disrupted spawning behavior in females bled during nesting season. By 2015, over 500,000 crabs a year were being bled, the majority of them females, while an alternative to this with the same efficacy exists. 2 harvests, one for bait, one for blood, neither coordinated, neither, for years, meaningfully regulated, and between them, the eggs vanished from the sand. The first response was simply to notice declines. In the late 1990s, biologists at the state and federal level began documenting what crab harvesters and birdwatchers had already seen. The beaches were emptier. Spawning surveys, shorebird counts, and crab egg density transects told the same story from different angles. The Atlantic States Marine Fisheries Commission had managed horseshoe crabs under a coastwide plan since 1998. But early quotas for their use as bait were high and largely voluntary. The real turning point came incrementally. Quotas were lowered. New Jersey and then Delaware imposed moratoriums or severe restrictions on female harvest. In 2012, the Atlantic States Marine Fisheries Commission took a step that was unusual in fisheries management. It adopted an Adaptive Resource Management Framework, the ARM. It explicitly tied horseshoe crab harvest levels to the population of red knots. The crabs could not be managed in isolation from the birds that depended on them. The ARM works like this. Each year, researchers estimate horseshoe crab abundance using trawl surveys and spawning beach counts. Trawl surveys are when nets are dragged along a specified area for a specified time, and the resulting species count is extrapolated for an area. Simultaneously, the U.S. Geological Survey estimates the red knot stopover population at Delaware Bay through a MARC resite study. Those two numbers feed into a model. The model recommends an annual harvest level. The maximum the framework can ever recommend is 500,000 males and 210,000 females. But in practice, when knot numbers are low, the model drives female harvest toward zero. Since 2012, female horseshoe crab harvest for bait has been zero in the Delaware Bay region. Male-only harvest has been permitted, up to 500,000 per year. Because males contribute less to egg production, they're less ecologically critical to the shorebird link. The 2025 specification is 500,000 males, 0 females. The biomedical harvest operates under a different regulatory regime. The management plans track collections and require reporting, but they do not cap the number of crabs bled. No caps at all. A potential exit from this dilemma appeared in the late 1990s, when scientists cloned the horseshoe crab gene responsible for detecting bacterial contamination. The resulting synthetic test works without any animal product. A decade of validation studies demonstrated it matches or outperforms the natural version. In May 2025, the US formally approved the synthetic alternative for use, a regulatory green light. If the pharmaceutical industry follows through, it could reduce horseshoe crab bleeding by 90% or more. But the industry has been slow to switch. The natural test is entrenched in testing protocols, supply chains, and regulatory filings. Switching requires revalidation. Even just this month, a group in Massachusetts is considering deregulating even further. Conservation groups have launched scorecards tracking manufacturers' progress. Pressure is building. But for now, hundreds of thousands of crabs are still bled each spring. Consider our male, the one who clasped onto a female under the full moon. He survived the bleeding and was dropped back off, drifting off to patrol the shallows. He feeds now in the soft bottom a few hundred meters offshore. Clams, worms, bits of dead fish, anything his appendages can shred and his leg bases can grind. He has no jaws. He eats by walking, crushing food between the spiny bases of his legs and passing it forward to his mouth. He is durable, built to tolerate wide temperature and salinity ranges, to simply outlast whatever the world throws at him. For 450 million years, his kind has succeeded by producing enormous numbers of eggs and waiting. The crabs are recovering. Abundance indices from trawl surveys show a clear upward trajectory since the mid-2000s, with 2023 estimates approaching 1990 levels, the benchmark year before the decline. The estimated population of Delaware Bay horseshoe crabs now stands at roughly 16 million adult females and 40 million adult males. The bait harvest that nearly collapsed the population has been partially reined in. From a peak of 2.5 million crabs in the late 1990s to 500,000 males and 0 females today, a reduction of roughly 80%. The red knots are not recovering. Stopover population estimates have stabilized around 40 to 45,000 in recent years, still well below the estimated historical population of around 100,000. The disconnect suggests that Delaware Bay may have only been one of the problems they were facing. The bird's fate is being written across an entire hemisphere. Breeding success in the Arctic, survival at wintering grounds in Tierra del Fuego, food availability at other stopovers, or maybe, like so many other things, with all the effort, we just can't put it back to how we found it. In 3 of the last 6 years, cold water intrusions linked to changes in the Gulf Stream have disrupted horseshoe crab spawning timing at Delaware Bay, meaning that even when crabs are present in sufficient numbers, their eggs may not be available on the beach when the birds need them. The approval of synthetic alternatives to horseshoe crab blood is a genuine breakthrough. But slow adoption by pharmaceutical companies is confusing. And then there are the beaches themselves. Sea level rise, intensified storms, shoreline hardening, bulkheads, riprap, seawalls built to protect coastal property. These are eroding or eliminating the gently sloping sandy beaches horseshoe crabs need to spawn. The conservation of horseshoe crabs in Delaware Bay is, on balance, a partial success. One of the clearer examples in marine management of harvest restrictions producing measurable population recovery. The crabs are coming back. The birds are not. At least not yet. Take yourself to a Delaware Bay beach in late May. An hour before high tide, just as the light goes. Then they come. Dark domes surfacing in the shallows, riding the tide in, silent, unhurried, ancient beyond comprehension. The horseshoe crab navigates by magnetic memory, by chemical taste, by the pressure of tide and the angle of light through water. His spawning is timed to the moon, calibrated to temperature, executed with legs and tail and the patient architecture of a body unchanged since the Triassic. Nothing in that sequence requires permission. Yet, as we change the world around him, sometimes directly by harvesting his blood or limiting the chance that he's used for bait, sometimes indirectly by emitting fossil fuels and warming his water, we have to wonder, how much can he bend? And how much more until, as may happen with the red knots, we are the event that ends a 500 million year dynasty. To close today's episode, let's let Walt Whitman weigh in. A poet who lived his last 2 decades on the banks of the Delaware, watching the same water, the same tides, the same seasonal arrivals that still govern this bay. These lines are from Leaves of Grass, written by a man who spent his evenings crossing the river on ferries for no reason except to be on the water. On the beach at night alone, as the old mother sways her to and fro, singing her husky song. As I watch the bright stars shining, I think a thought of the clef of the universes and of the future. A vast similitude interlocks all spheres, grown, ungrown, small, large, suns, moons, planets. All distances of place, however wide. All distances of time. All inanimate forms. All souls. All living bodies, though they ever be so different. All gaseous, watery, vegetable, mineral processes. The fishes, the brutes. All nations, colors, barbarisms, civilizations, languages, all identities that have ever existed or may exist on this globe or any globe, all lives and deaths, all of the past, present, future. This vast similitude spans them, and always has spanned, and shall forever span them, and compactly hold and enclose them. Thank you for listening to this episode of the Wild Systems Podcast. If you enjoyed the show, please subscribe and leave a comment. If you want to read the article for this episode, go to the Ecological Resilience Project's website. To engage further with the team who produces the Wild Systems podcast, head over to our website. Join us next time as we follow another thread in the web of life and ask again what it costs and what it's worth to let the wild things keep doing what they've always done.